Hi folks, welcome back to Math with Captain Rod. The purpose of this video is to demonstrate how to use first and second derivatives to tell intervals of concavity and to look for relative extreme values or relative extremas. So we're going to look at the function y equals tan x minus 4x on the interval minus pi over 2 to plus pi over 2. We're going to check it for concavity, we're going to look for inflection points, and we're going to look for extreme values. So let me talk about the extreme values. There's obviously one here, another one here. This looks like a relative max right here, relative min at this point. I'm going to go ahead and start by looking for those points. Key feature at a relative min or max is that the tangent lines have zero slopes at those points. And again, the slope of the tangent line is described by the first derivative. So we're going to calculate the derivative of this function. So the derivative of tan x is secant squared x. Now if you don't remember that, that's fine. You can get that by writing tangent sine over cosine and applying the quotient rule. Derivative of 4x is 4, so minus 4. All right, so the derivative of that function is secant squared x minus 4. Now, to find the relative extreme values, we need to know where that thing is 0. And I'm going to go ahead and rewrite it. 1 over cosine squared x minus 4 equals 0. Because secant is 1 over cosine. And then we're going to add the 4. So 1 over cosine squared x equals 4. And then I'll just reciprocate that. Cosine x equals 1/4. Cosine squared x equals 1/4. Square root both sides. Cosine x equals, now when we square root this, we're going to get plus or minus 1/2. And again, this is occurring because when you have equations like, just, take a little break and talk about this. If I have an equation like x squared equals 4, there are two values of x that solve this, plus 2 or minus 2. So cosine squared x equals 1/4. There are two values for cosine x that solve this, plus 1/2 and minus 1/2. So let's see, cosine x equals 1/2. The inverse cosine of 1/2 is pi over 3. Now, the other one is cosine x equals minus 1/2. So the inverse cosine function is defined between 0 and pi. If you're not familiar with inverse cosine function, where it's defined, I would encourage you to go back and look at my videos on inverse trig functions. So cosine x equals minus 1/2. When we take the inverse cosine of both sides, we're looking for an angle between 0 and pi that has a cosine of minus 1/2, and that angle is 2 pi over 3. I've got to stop this for a moment. I just want to think about these results before I move on. All right, so I was just kind of mulling the results over. So this is fine. This guy right here, x equals pi over 3, I'm sure that's this value right here. Now, the second one, 2 pi over 3, is over here somewhere. And that's not in the domain that we've been asked to discuss in this problem. This guy right here is actually going to come from the solution of this equation again. This equation, cosine x equals 1/2, has two solutions. X could be positive pi over 3 or minus pi over 3. Also solves that equation. Now, the minus pi over 3 is not in the domain of the inverse cosine function, but it is in fact still an angle that solves this equation and correlates to that guy right there. It's just that your calculator won't give you the minus pi over 3. This is one you'd have to know just from knowledge of trigonometry. So the cosine x equals 1/2, x equals inverse cosine of 1/2 will kick out pi over 3, whether you know that knowing your trig functions or whether or not you use the calculator's inverse cosine function. The other solution is coming from the fact that the cosine is an even function. Cosine of minus pi over 3 also has a cosine of 1/2. That's that animal right there. All right, the y value here, the min value, is we can get by just taking our pi over 3 and running it through our function. So that's going to read tangent of pi over 3 minus 4 times pi over 3. I don't remember my tangents of all trig functions, but I know that I can write this sine of pi over 3 over cosine pi over 3. Minus 4 pi over 3. Sine of pi over 3 is root 3 over 2. And then we're dividing that by 1/2. So this thing's equal to square root of 3. So this value right here is equal to square root of 3 minus 4 pi over 3. This value, and because I want to move on, based on the symmetry of this problem, well, I better write it out. All right, so this one here is going to equal tangent of minus pi over 3 minus 4 times minus pi over 3. So this one's going to equal root 3. Tangent of pi over 3. The sine is now going to be negative. The cosine is still positive. That thing is going to be minus root 3 plus pi over 12. So there are the relative mins, relative max. This one's a relative min, this one's a relative max. I'm going to now work on the inflection points. Before I do, I'm just going to pause this and give the folks with me here a chance to chat. So we've had a little discussion about this problem. At this point, I'm going to get rid of this stuff and now start working on what I need to talk about the inflection points. So I don't need any of this anymore. I do need that derivative though. All right, so the inflection points, as I look at this, it looks to me like there's only one inflection point, which is there. It's probably the point 0, 0 based on the graph. And notice I'm getting this just by observation. This thing is concave down to this point, and now it's concave up. Now, as far as how we actually find it, the inflection points are found by looking at the second derivative. So when we differentiate this function, this has to be chain ruled. There's the secant part and the square part. So differentiation of the square is going to be 2 secant x to the first power. We don't generally write the 1. Times the derivative of secant x. And the derivative of secant is secant tangent. So this is going to be secant x tan x. And again, if you don't remember that, you can write this 1 over cosine and you can quotient rule it. Or you can write this cosine to the minus 1 and then chain rule it. Either one will yield this derivative. To get the inflection point, we need to know where that derivative is equal to 0. The 2 can just be divided out, and we're going to be left with secant squared, and I'm going to go ahead and write that 1 over cosine squared. And then tangent is sine over cosine. So again, in this step, I've divided a 2 out. 0 over 2 is still 0. Secant times secant is secant squared. But if I want, I could write that 1 over cosine squared. And then tangent is sine over cosine. This has only one, this solution. We can multiply both sides by cosine cubed. Sine x is 0 at x equals 0. Now this thing has more inflection points. X equals pi, 2 pi, 3 pi, all are zeros of that equation. Going the other way, minus pi, minus 2 pi, etc. all solve this. So this function apparently has a bunch of inflection points. We are asked to find only ones between minus pi over 2 and pi over 2, and that's that one right there. So the inflection point is that thing right there, x equals 0. So I think that we found pretty much everything that was asked for in this problem. We found the inflection point. We found the relative mins and relative maxes. Hope this video helps demonstrate this stuff. Have a great day.